All right, guys, when we left on Friday, this is about the spot we had stopped, and I had you guys work on these 6 examples here in the notes, and I kind of want to go over them. We talked about the first 3, but I kind of want to zoom into these last 3, so D, E, and F, and talk about the notation that we were covering, what exactly you need, and then how, to remind ourselves how to use table A. So right now we're specifically working with z-scores, which means we're on that standard normal curve, and I'll have to sort of redraw the curve every time we do this, and I'll have a copy and paste on this video recorder. So we'll get our normal curve. Remember, when we're working with z-scores, mean is 0, standard deviation of 1. This is all the notation that goes into that. I know it seems a little redundant to label it, but this up here is necessary just because we want to make sure that we do say this is a normal distribution, since we'll be working with some other distributions here in the future. Now we want to find from to the right of negative 1.47. So if we were to mark negative 1.47, maybe right about there, I'll even put the number right there just to indicate what it is, or that mark is, and then we will shade everything to the right of it. Now the problem is when we go to the table, let's list out what we want to find. We want to find everything greater, so then to the right of negative 1.47. But as we learned on Friday, the table A only finds z-scores to the left. So we'll need to essentially find this space in yellow on the table A, and then we'll need to subtract it from 1. Now, there's some extra notation that goes into this, and we'll clean up this notation, or at least make it shorter later. But for now, I want us to practice it, because you will see it in free responses and multiple choice questions and so on and so forth. So it's something you do need to just at least be able to recognize and possibly write on your own. So the problem is we can only find, like I said, the z-score to the left. So we're going to indicate that, okay, look, yeah, we want to find greater than, but when we go to our table, we're actually going to find z is less than negative 1.47, right? I mean, that's what table A is actually going to give us, that yellow area, everything less than that. And we're going to take that away from 100%. This step is a really tough one notation-wise for a lot of students, just because we're flipping the inequality to indicate that, look, we're actually finding the other side. So hopefully it's a notation you can get comfortable with as we go on. And again, this one minus only needs to happen when we're finding things to the right. All right, so I'm checking out table A right now, and I found negative 1.47 on there, and it was 0.0708. So we'll take that away from 100%, and we should get 92.92% of the graph. So there we go. There's all the notation you need, the graph shaded. The yellow part you don't need. I just was marking that so we could see it on the video. So that's not something on the AP exam or on a test or anything you would need. But you certainly need the red part, the shaded red part of the graph. All right, let's go over here, and we'll take a look at this one. Let's see if I can shrink this down too. I'm just kind of looking here at all the tools I have, but I might leave it there for a second. Okay, so let's check out this one. Again, I'm going to get my graph on here. This is an in-between problem. A little bit of notation that goes into this one that's a little bit different too. And all the notation's doing is just describing your thought process as you go through. Let me get my graph here. So 4.2 was way up here. I mean, just way up there, even maybe further than that. And then 0.21 was pretty close to the mean, and we're trying to find everything in this area between them. So, of course, our notation is from 0.21 to, and we'll put our z-score there, 4.2. Now, the idea, let me label my 4.2 and my 0.21. The idea is to find 4.2 on table A, which we found earlier actually on these 6 problems, but is to find 4.2. Let me grab a highlighter on table A, which will give us all of this, right? That's what the table A will give us. But then we want to go find 0.21 on the table, which will give us all of this area for 0.21. If we subtract those two, we'll be left with the yellow part, because we're taking the blue part away from the entire yellow part. So in other words, in terms of notation, what we're going to say is we're going to say, well, here, we're going to find z is less than 4.2, and we're going to subtract away the proportion that z is less than 0.21. And so we're really just breaking down that compound inequality and splitting it up into the subtraction problem that we're going to do. So we'll get those two values. Of course, 4.2 is off the table, so that's 100%. And then when we find, let's see here, 0.21, I got about 0.58. Let me make sure I get this number correct here. 32, right? So we'll subtract those from one another, and we should get 0.4168. And there we go. All right, 41.68% then. All right. So yeah, so notation-wise, that looks good. All right, and then this one, this is just almost the same problem, except it is an in-between problem. We just worded it a little bit differently. I even had someone in class that day ask me, okay, when we say 1.5 deviations away from the mean, are we saying on both sides? And the answer is yeah, we are, right? So if you're within 1.5, which is probably right about here, you could be above or you could be below. You're within 1.5, somewhere in this region right here. So again, same sort of notation where we're going to list, whoops, let me not use an x value there, a z value. We're in between these two. And then we're going to, of course, take the upper 1.5 and subtract away the lower negative 1.5. Sorry, I ran off the screen there. And we'll find those two values. Now, if you're kind of noticing, and I don't think we've run into this yet, there is obviously symmetry within this graph, mainly because it is a symmetrical graph, right? So, you know, sometimes, let's look here. What is 1.5? That is 0.9332, and negative 1.5 is 0.0668. Right, so we'll take those away from each other, but you'll notice that those numbers are actually complements of each other, right? So the reason being is they're on the exact same spot on opposite sides of the graph. So it's like once you find one, you could technically just reason out the other one, the 6% versus the 93%. But yeah, there you go. All right, so practicing z-scores, right? These are nice because they don't have any context to them, but obviously in this class we care more about where this type of statistics is going to be used as opposed to just repeating it and doing it again. So what we want to do is we want to kind of switch from z-scores to problems in which we use this normal probability table to find stuff. So in the class of 2016, more than 1.6 million students took the SAT. The distribution of scores on the math section, which was out of 800, follows an approximately normal distribution with a mean. So we'll get our table down here. Also, let me fix that. There we go. All right. That x-axis will just have to stay that way for a moment. All right, so a mean of, what do we have here? 508 and a standard deviation of 110. And so we'll put that this is an approximately normal one, again, listing the mean and the standard deviation. All right. About 1% of students who took the SAT scored less than 350 on that section. All right, so we kind of just so we're able to put our mark on here, we need to determine exactly how many, in our mind, how many standard deviations 350 is, obviously below 508, which is our mean. Since the standard deviations are 110 apiece, obviously one standard deviation would be 508 minus 110, which is going to be 398. So 350 is over one standard deviation from the mean. Maybe right about here. We'll mark that as 350. And, of course, we'll label our graph SAT score. Right? If you're going to create a graph that is based around the context of the problem, you want to make sure you label your axes so we know what those numbers mean. Otherwise, if you're using z-scores, which I might bring up later, I mean, a lot of people just tend to like to draw their normal curve as a standard normal curve around z-scores, so that way they don't have to worry as much about labeling, because clearly with z-scores they don't have units, so you know it saves you a step. But yeah, if you do it within context, you need to label. All right, so let's get our notation here. We want to see that P is okay, and this time we're going to say X is less than 350. Now, there's a big switch here that you may have noticed. I had been using the variable Z, mainly because we had been working with Z-scores, but now I'm using the variable X. Since we have a new variable in here, we probably want to define what it is. X is the score on the math it's SAT, not ACT, but the SAT section. All right, we want to know the probability that a student, or about what percent of students, I should say, scored less than 350. So what we can do is we can either do it within the notation or we can come off to the side, but we do need to come up with the z-score so that we can find this on table A. So our z-score is our value, which is 350, minus our mean of 508, and then divided by the standard deviation of 110. Right, so kind of putting everything together that we've been doing, and hopefully now we can find, give me just 1 second here. So I got about negative 1.36, which means our z-score is going to be down there, which actually makes a lot of sense. We said it was going to be more than one standard deviation below the mean, because clearly 350 is more than 110 away from 508. So yeah, there we go. So we'll say, okay, that all equals, and then notice the switch in variable. Z is less than negative 1.36, and here we go. All right, so we've got that all listed. This is a less than problem, so we don't have to do a 1 minus or anything like that. We hop to our table, we find 1.3, and then scroll over to 6, and I'm getting about 8.69%, and there we go. And if you're asked to interpret, and feel free to write this down. It's just harder for me to write on here, so I'm going to just say it. And if you want to add this to your notes, you can. Say about 8.69% of students scored less than a 350 on the math section of the SAT. And there we go. All right, so not many, but there we are. All right, so let's keep practicing a few here, and then we'll go. So we've sort of talked about a lot of what is already in here and how to do this. So I'm just going to kind of breeze over this quickly. Obviously, when we brought this problem up at the beginning, the Gary, Indiana, and, them having it was for 7th graders, but the average being about 6.8. This was from the beginning of the section, so we're just revisiting this. Obviously, we're going to start every problem with a picture and kind of mark where we're at. And we're curious, okay, what proportion of students then are scoring above the 9th grade level, right? So because it's an above then problem, or greater than problem, we'll need to do 1 minus. So we start with the picture, with the mean and the standard deviation, our boundary line, and then we shade the area to the right. After we do that, we then need to standardize that value. You're not moving on with this problem until you figure out where 9 is as a z-score, right? So we then calculate, okay, let's see here, z is, and then we take 9 minus 6.84, and we divide that by the standard deviation of, I gotta figure out what our standard deviation was here. 1 second. So we can take 6.84, which is our mean, and pretty much subtract 5.29, which is 1 standard deviation below the mean, or 8.39, doesn't matter. But when we subtract those two numbers, I get 1.55. So I know the standard deviation on that graph is 1.55, and that comes out to a z-score of about 1.39. And that does not round up, but if it did round up, you would want to round it up, right? You only go to 2 digits with z-scores because that's what table A goes to. So, of course, we do that, but when we go to table A, we find it to the left of 1.39. So we do 1 minus whatever that is, which was, about 91.77. That's what the proportion is for 1.39, so 1 minus that 91.77 is about 8.23% or 0.0823. And there you go. So we can easily find that out. I'm skipping a little bit of notation here because this is just sort of review, okay? Common mistake, just real quick before we move on, is to look up a z-score in Table A and report the entry corresponding to that z-score regardless of whether the problem asks for the area to the left or the right. Of course, if it's asking for it to the left, yeah, you're going to report the one right from Table A because everything on that table is to the left, but you just have to be so careful about, okay, is this a right-handed problem or a left-handed one, because we want to make sure we get that right. All right. All right. I noticed that I didn't leave us a lot of space on this next problem. So I'm going to zoom in here. Actually, let's do this. I might bring this down. I need to fix this in the notes. I'm just noticing. Let's do this. So back to the SAT problem. We've got a normal curve, same mean, same standard deviation of 508 and 110. So let's draw our graph right here. We'll label it very quickly. We've got our mean of 508, standard deviation of 110. It's approximately normal with a mean of, again, 508 and 110. And we'll say SAT score. And again, these are a lot easier to draw on paper. They're actually much easier to even draw on Notability. Like I said, I'm not using that right now. So as you get better, as you practice them, you'll get better at drawing them. All right, so this one was asking about, the University of Michigan has recommended that the math SAT score is at least 730. So the phrase at least is indicating that this is a greater than problem. So 730, we realize very quickly, is about 2-ish standard deviations above the mean. So maybe somewhere out here, and we're going to shade this little tail. Let me extend that tail out a little bit. And so our problem is, the probability is at least 730. And based off the way that's worded, at least usually is an inclusive phrase. So we want to put an equal to on our inequality. But we learned the other day that's not going to make a difference when it comes to finding probabilities, because again, we're finding area under this curve, and there is no area at a specific point. So including 730 versus not including 730 is not going to make a difference. We're still going to look up that same z-score. It's not going to add any additional probability. So we'll convert that to a z-score real quick. We want to say z is, and then we'll do 730 minus 508 divided by 110. And let's get a z-score. So I got almost exactly 2 standard deviations, but 2.02. So we'll say, all right, well, we want to find the probability that the z-score is above 2.02. But since this is a greater than problem, when we go to Table A, it will report the probability that it is less than 0.0202. So we need to indicate that that's what we're going to find on the table, and we're going to take that away from 100%. So there's that notation that sort of gets the best of students. So make sure we practice that one and have that one down. Let's find that z-score, 2.02. It should be a pretty big probability here. So I'm getting about 97.83. So 1 minus 97.83. And so that's going to leave us with about 2%, 2.7, or 2.17%, 2.17% there. So yeah, a pretty low amount of students, right, would achieve that score. And again, as an interpretation, we would expect the proportion of students who score above a 730 on the math section of the SAT to be about 2.17%. All right. And then last but not least, and I kind of just saved this one as a drawn out, but we'll do one here in a second. I wrote this next one out about the Gary, Indiana. Finding those in-between probabilities to make sure that you're taking the area from the upper bound minus the area from the lower bound to get the in-between. And so you can, again, need to convert them to z-scores and things like that. So let's do one with the SAT problem one more time, and we'll get rolling here. So, all right, see here. We'll get our normal curve. I believe this is the last time we'll draw this one. Same mean, same standard deviation, still approximately normal. And this time we want to know what percent of students score in the 500s. And this one's interesting. You can't earn decimal point values on the SAT, but, there's this question of, okay, so in the 500s, that means 500 to 501, all the way up to, I guess, essentially 599. But in my mind, there is data between 599 and 600. There's a proportion of people that theoretically could score in that range. And so, in my opinion, we need to go up to at least 600. And remember, going up to 600, whether we include 600 or not, doesn't affect the probability at the end of the day because there's no area at exactly 600. So my thought is, okay, let's go from 500, which will be right about here, to 600, which will be a little bit below one standard deviation. Maybe, just marking it right about there. There's 600, and we're trying to find this area here. So I would say, okay, the proportion of students that score from 500, and I'm going to include 500 because 500 is a valid score for this, all the way up to 600, not including 600. But again, it's not going to make a difference. But I think that's a fair notation, and I think we should find the z-score for 600 to make this work. So we've got two z-scores to find. We've got our 500. So let's do that one first. 500 minus 508 divided by 110. And then we've got our z-score for 600 minus 508 divided by 110. By the way, finding it for 500 to 599 would result in a different answer. And so I think it's important that we have that up to 600. Let's go ahead and calculate these. All right, so I got negative 0.07 and the other value, let's see here, 0.84 as my z-score. All right, so let's get all this notation correct and think about how we need to do this. So, number one, all right, we want to write the same notation that we have there, but in terms of z-scores. So from negative 0.07 to z, right, we're converting this to z-scores, all the way up to 0.84. Then we want to indicate how we're going to actually compute this problem. So we want to go, find the probability for z being less than 0.84, and then we want to take away the lower probability of z being less than or equal to negative 0.07, right? Because that's what we would do. We take that upper minus the lower to find in between. And let's go to table A and let's find both of those. All right, so my first value, I found 0.7995. For this lower one, I found look here one more time, 4721. And if any of these are off, just let me know. I am looking on a much smaller screen at that table A, so it's probably likely that I could, very likely for me to look at the wrong spot. But let's go ahead and get those. 0.7995 minus 0.4721, and we get about 32.74%, so about 32.74% of people. And there we go. Okay. So yeah, it's quite a bit of writing, but even just a basic SAT problem kind of shows you the power of what you can start doing with this. You can start finding the probabilities of specific things happening. So speaking of that, I want to start to head into something kind of neat. I want to also show you how you can use Table O to work backwards. That's the first thing I want to do. And then I actually want to show you how we can potentially toss Table A out completely by using our calculator. All right, so what this next topic or concept will do, will allow us to take a percentile and essentially find the value for that percentile. So for example, if we go back to the Gary, Indiana, let's imagine we want to know, okay, what was the score of someone on this vocabulary test at the 90th percentile, right? So in other words, we know that they scored better than 90% of the people. So we know that if we were to sketch a normal curve based on the z-scores, that 90% of that curve would be shaded because that's the percentage of people they beat. Now, remember, Table A will give you all of these values or all of these proportions. So what we can do is we can hop to table A and we can search, and we know it's going to be on the positive side because it's above the mean, 90% is. We can search on that positive side for the closest number to 90% that we can find. For me, and it should be for you also, that is 0.8997, which corresponds to a z-score of 1.28. So I'm just kind of tracing that over on table A. And it takes a while. I mean, you got to search through all those percentages, but find the one that's closest. But it looks like z is equal to 1.28. So now that we know that, 1.28, we can do what we did the other day, where we take the z-score calculation, and since we actually know the z-score for this problem, we say, okay, let's set that up, set that equal to. We'll take the mean and the standard deviation from this situation, and we'll find the value. So we set this up like this. Let me go get the mean and the standard deviation here, and I'll be right back. So I went back to the other page, and it looks like the mean was 6.84, and the standard deviation was 1.55. All right, so we're just going to unsolve this, and so we're going to take 1.28 and multiply it by 1.55, and then we are going to add over 6.84. And that gives us an x value of about 8 point, we'll just leave it at 8.82. They seem to have used 2 decimal places in the problem. And our units, I believe this was just the, what was the abbreviation or the acronym here? ITBS score, which means they were reading, if you're at the 90th percentile, you were reading at about almost the 9th grade level, about 8.82. All right, so there we go. Okay, so we can work backwards. All right, so let's try one. After accelerating for about 20 seconds, a DeLorean sports car has a wide range of speeds that it can achieve depending on the traction. So the distribution of speeds it can achieve follows a normal distribution where the mean speed is 80 and it has a standard deviation about 7.7. So Marty wants the next acceleration to be in the fastest 15% of all possible speeds. How fast will the car have to go? Right, so considering he wants the fastest 15%, we are on the right-hand side here. That's not going to make a huge difference because we're not finding a probability this time. We're given the probability, the fastest 15. But it is important to note that because a lot of students will get confused when we say 15%, they might accidentally find this 15% down here. That is the slowest 15% of speeds. So we'd want to be very careful on which side of the graph we're marking because clearly you could see, on the problem we're working on, I'm going to get a positive z-score. However, if I make the mistake of marking 15% on the graph, I'm going to get a negative z-score. So in other words, we're really at the 85th percentile. So 15%, top 15, means that we're at the 85th percentile. So what we need to do is when we go to table A, we are not going to look for 15% in table A. If we did that, we would end up on that negative side over there, and that'd be an issue. We're actually going to look for 85%. So I'm hopping to the table here, and it looks like the closest value I can find is 0.8508, which is a z-score of 1.04. So our z-score is 1.04 for the 85th percentile. So let's go ahead and do the math here. We've got 1.04 equals, we want to find what that speed is. And what's our mean here? Our mean is 80, and our standard deviation is about 7.7. All right, so we'll take 1.04. We're going to multiply it by 7.7, and then we will add over 80, and we will get 80. Let's see here. 8 point, well, really 0. I guess we could round that to 1 miles per hour then. So if he were to be able to achieve that speed, he would be at the 85th percentile. He would be in the, anything above that essentially is the top 15%. Again, if you want to put that interpretation in your notes, right, to achieve the top 15% of speeds, he would need to go 88.01 miles per hour or faster, right? So there we go. All right, Perfect. So that's everything we need to know about z-scores and table A, except for one major thing is how do we do this in the calculator? And I'll let you decide if you like this a little bit better or not. So I want to do kind of a big problem here on Rafael Nadal, tennis player, if you didn't know that. So we're going to look at his statistics from 2008 when he was sort of first getting into, I don't know if that was his beginning of his tennis, but certainly a long time ago here. And we want to look at his serves from that Wimbledon tennis tournament that year. And I want to do this one in the calculator. And so I'm going to kind of talk you through the calculator buttons. If you need to pause right now and grab your calculator, please do that. And we'll look at how a lot of this notation can be shortened by using it. All right, so Rafael Nadal, he would average 115 miles per hour on his first serves, and we're going to assume that the distribution of first serve speeds is normal with a mean of about 115 and a standard deviation of 6. So I went ahead and I gave us the graph here so we didn't have to keep redrawing, although we are going to label, okay, I think our units would be miles per hour then, standard deviation. What was the standard deviation? About 6 miles per hour. And of course, this is approximately normal. Well, and you know what? I've got this notation. Let me erase this up here. So let's just use this right here. We've got a mean of 115 and standard deviation of 6. All right, so our goal here, all right, is to figure out what would you expect to be between two standard about what percent, would you expect to be about two standard deviations of the mean. So we're looking from above and below. So essentially we want to find the proportion of serves that are, let's see here, what do we got, 121 and then 127 is our upper, and then 103 would be our lower, so to 127. And that should be two standard deviations below and above the mean then. So let's calculate that. Now, usually we would go to we would calculate the z-scores at this point. We would also do our notation for like how we're going to use table A, where we do the upper bound minus the lower bound. There's a lot of notation that goes into these in-between problems. But like I said, I want to show you how to get rid of table A for a moment and just use your calculator. So here's what we're going to do. We're all going to go to the distribution part of the calculator because we are working in a normal distribution. So that's why that button is called distribution. And you will notice it above the vars key, the variable key there, next to program, next to clear. But you'll see DISTR above the vars key. So you do need to hit second vars. And in here, you will see two things right at the top. You'll see normal PDF and normal CDF. Now, we will exclusively work with normal CDF. I don't think I've ever used normal PDF. I don't really think it has much of a purpose. If you're curious, look into it. I'm happy to look into it for you, but we will stick with normal CDF. And the reason being is the C stands for cumulative, meaning, you know, we want all of the area to the left or all of the area to the right or all of it in between, right? So we want to stick with that cumulative one. So here's what we're going to do. Go ahead and hit enter on normal CDF. And if you have an updated calculator, which I hope most of you do, it should bring up a menu where it says lower, upper, mean, and standard deviation. So what I want you to do on your notes, this is the one downfall of normal CDF, although I think you're going to like this route a lot better, is we're going to write normal CDF, okay? But because it's calculator driven, we have to label each thing on test and AP exam. The readers of the AP exam assume essentially that if you're not going to show your work, if you're not going to show your notation, then they at least want to know that you know each of the things in normal CDF. So we'll put lower. Okay, let's think about this then. Our lower bound is actually going to be 103. That's the slowest serve we're considering here. Then it'll ask for upper. Our upper bound will be 127. And then, of course, our mean will be, what was our mean here? 115. And our standard deviation will be 6. And you can use colons there. In fact, let me switch these equal signs to colons instead, since I had been using that on lower and upper. There we go. I switched to equal signs. And so let's type that in. So we will say 103 to 127 with a mean of 115, and a standard deviation of 6, and we'll hit paste. And it should come out with a probability. We're at about 95%. let's just call it 45%. And there we go. And that's it. That's all the work that needs to be shown on that one. The beautiful thing about normal CDF is it controls the lower and the upper bound. Let's shade up here too. I did forget to kind of do that while we were talking through the problem, and I don't want to always go back and check things that I did and did not do. But yeah, there it is. It takes that all out. So yeah, no more 1 minus. We'll get to a greater than problem in a second. No more P of this minus P of this, because we're finding in between. Really just normal CDF will knock out the whole problem for you. Also, you can run normal CDF with z-scores if you want to. Obviously, we use the contextual numbers here, 103 and 127, but had we converted 103 and 127 to z-scores, or maybe they handed them to you in z-scores, I don't know, you can let your lower be a z-score, your upper be a z-score, and then, as you probably realize, your mean would be 0 and your standard deviation would be 1, because that's the mean and the standard deviation on a standard normal curve where we work with z-scores. So pretty cool. All right, so let's go to the next page here and see what we have. All right, so on the next page, we're going to look at a couple different problems here where we might have to find one to the right and one to the left and things like that. So go back, serves at 115, standard deviation is 6, and we're interested in the number of serves less than 103. All right, so let's go over here and let's label so we'll put our mean of 115 or standard deviation of 6. Of course, it's approximately normal with 115 and 6. And then 103 would be exactly 2 standard deviations. And we say this. Now, here's the interesting thing. This lands on a perfect standard deviation mark, right? Because 115 minus 6 is 103, right? So theoretically, if we were to use the 68, 95, 99.7 rule, I'll let you refer back to it, but we should see this value come out to about 2.5%, right? There's 2.35 between 2 and 3 standard deviations, and then 0.15 after that. So I'm expecting this to come out to 2.5%. Let's see how accurate that 68, 95, 99.7 rule is that we learned the other day. But again, we're going to use normal CDF on this problem. So what we'll do is we'll say, okay, the proportion, we want to find the proportion of serves. So X is less than 103. So they're slower than that. I'm not going to say equal to because it does say less than. Let's go to normal CDF here. We'll do it in our calculator in a second, but let's just kind of think through this problem. And this is the power of shading the graph, at least early on as a stat students, and this is what they're looking for on the AP exam, which is why they want you to draw and shade your graph always. My rule of thumb is anytime you calculate normal CDF, you should probably draw a graph and shade it, right? So let's do our lower bound. This one's a little tricky. This one goes on forever, right? So this shading, let me draw a little arrow, will continue because there's sort of an asymptote there that curve will never technically touch that x-axis. So what we need to do is we need to say this will essentially go to negative infinity. I don't know, negative infinity standard deviations or negative infinity miles per hour for his serve. Now, most people say, well, isn't the slowest serve he can make 0 miles per hour? And yeah, like in context, yes, but in theoretical sense, we want to make this go to negative infinity. And there are a couple different ways to do that. But the easiest way is just to say, let's just plug in a really big negative number. I usually use negative 10,000, negative 100,000, something like that. Just a ridiculous, he's never going to do that serve or obtain that mile per hour. That is negative infinity. Our upper bound this time, since the highest we want the serve to be able to go in this situation is 103. That's where the shading stops. And then, of course, the mean is same thing, 115, and the standard deviation is 6. So let's go to second vars here, or second distribution, and let's plug this in. We've got negative 10,000, and then we've got 103 is our upper bound, and it should have the same mean and standard deviation from the last calculation. And here it is. Here's our probability. It is 227, which is about 2.3% if we were around that. So really close to that 2.5%. But, that 68, 95, 99.7 rule is sort of a rule of thumb, not an absolute. So here's actually the percent that's below 2 standard deviations. So kind of interesting to see. It's not quite 2.5%. Okay, and there we go. So the opposite would happen on greater than. Like I said, the beautiful thing about normal CDF is you don't have to do 1 minus anymore. Normal CDF can find probabilities to the right. you would just let your lower bound be that lower number, and then your upper bound be infinity, so like positive 10,000 or positive 100,000, or yeah, I guess technically you could do 1e to the 99th power in your calculator. That's another way to indicate infinity. But yeah, you would be able to find that to the right. So normal CDF just has a lot of benefit. It takes away a lot of the pain and sort of the tedious nature of the notation and remembering when to do 1 minus, so highly suggest using it. Let's do this. Let's go ahead and I'm going to have you guys do these next two. One is a shading and labeling, and then the other is just trying it by hand. Again, I'm going to ask us to do it from time to time because of that. So in a moment, I'm going to have you pause this. Don't pause just yet. And I'm going to have you do those two just to kind of end this, and then you can work on the assignment. But I do want to show you one more function in the calculator that'll be useful for you from this section. There were problems on the last page in which we were given a z-score, and then we were asked to find what value was at that specific percentile or that specific z-score. And right now, we're just pretty much like going to table A. We're searching for the closest percentage we could find, and then finding that z-score and working that z-score calculation backwards. Well, since we're using normal CDF in the calculator, I want you to go back to second vars. Let's go to distribution. And you see right under normal PDF and normal CDF, there's a function called inverse norm. An inverse norm is really a great tool to use. Go ahead and click on inverse norm, and you'll notice it asks you 3 questions. So I want to revisit that Gary, Indiana problem from the last page, in which it asked about the 90th percentile. What would your grade level be at the 90th percentile? And I'll sketch this real quick. They were saying, okay, here's the 90th percentile. What is that? So what we want to do is we want to say, okay, well then, and it does work to the left, inverse norm does, but we know, actually, let me back up 1 second about that comment on the left. It does work to the left, except I think a few of you with really updated calculators may have the option to do left, center, right, and then you have the option to say whether you want the percentage to be to the left, the percentage to be to the right, and the percentage to be in between, aka the center. My personal one defaults to the left, but on this problem at the 90th percentile, we want the 90% to be to the left, so make sure you're selected to the left. If you did change that to the right, you would need to say 10% to the right. 10% to the right and 90% to the left are the same spot on your calculator, so just be careful on whether you have that thing selected to the left or the right, if that's an option on your calculator. Some of you guys might be sitting here thinking, I don't see a left, center, right on my inverse norm. What's he talking about? And that's okay. If that's the case, yours is just always defaulting to the left, which, is a good thing and a bad thing at times, and we'll see problems this year as we go through. But this was 90th percentile, which means 90% to the left. So go ahead and inverse norm. Let's list this out. And let's put the area at 90%, so 0.9. And please use a decimal, your calculator, any math really. When we're working with percentages, we work with them as decimals. And then we can either sort of use a z-score value, of 0 and 1. And if we do that, it will give us the z-score for the 90th percentile. So I went ahead and I hit enter on my inverse norm for 90% with a mean of 0 and a standard deviation of 1. And I got 1.28, which if you look back on the page, the last page, our z-score for that problem was 1.28. So that's kind of interesting. But I want to go back to inverse norm in here, and let's type in area of 0.9. And I actually want to use the mean for the problem, which was 6.84, and a standard deviation of, I believe, 1.55. So I want to plug this in instead. So mean 6.84, standard deviation of 1.55. We'll hit paste, and sure enough, we get a value of 8.8. If I round up, 3, which was the exact same number. We'll say that was I can't remember the vocab score. Can't remember the acronym off the top of my head there, but that's the vocab score. So yeah, normal CDF will find percentages. Inverse norm will find specific values for percentiles. So any type of problem I pretty much toss at you at this point can be done in the calculator. So essentially, I really hate to say this about Table A, but it's kind of an unnecessary tool at this point if you plan to go the calculator route, although some guys do like to have it on them, and it will be given to you on all the tests and AP exams moving forward, just in case you need it or want to refer to it, or maybe you forget where normal CDF or inverse norm are on the calculator. So All right, with that being said, that's everything on these. If this video ran a little long, hopefully you took it with you. I'm sorry. But yeah, there is a homework assignment tonight out of this section, so please look at the agenda. If you have any questions, shoot me an email, and I will see you guys soon. Thanks.